Welcome back, everybody. So this week we will be talking about inter-procedural analysis for the first time. So the idea is that while in the previous weeks I discussed how you can analyze both using type systems and using data flow analysis individual procedures, today we will be talking about how we can lift this to the analysis of multiple procedures, eventually covering the entire program. And the most important data structure that we need for this is a so-called call graph, which tells you about caller-callee relationships in your program. So it basically tells you which procedures or functions or methods might call one another at what places. And in languages that are object-oriented, or in general languages that support virtual method calls, this is also often paired with points to analysis, so that you can resolve virtual method calls to their actual call targets. We will be talking about that extensively this week. As a motivating example, let us look at this polyrec function again that we actually also discussed in the lecture on type systems. So as I explained, this is something that is not really typable through a regular type system, because the problem is you have this parameter g here, which in this recursive call is actually being used as an integer number. But in this initial bootstrapping call here, it's actually used as using null, which is a reference type value, is not a number. And so a type system that tries to assign any single type to this parameter here will fail, because basically that type here, it needs to be polymorphic. So it depends on the call site from which it is called. If you call it from here, it has to be an int. If you call it from here, it has to be a reference type. Type systems simply do not allow this. So you will actually need to have something more powerful. And static data flow analysis, if it's done interprocedurally, can basically give you something like this. So it would be able to conduct such an analysis and determine that this program is actually safe. Because the main difference is that data flow analysis, it never actually tries to assign a fixed type to this parameter. So basically it can treat this parameter polymorphically, which means depending on the context from which it is called, or depending on whether it's called from here or from there, it may actually make that distinction that in the one case, it's this type, and in the other case, it's another. And at the same time, you see that in order to do this also, you do need an inter-procedural analysis, right? So you need to be able to know, for instance, that this method call here will actually resolve to this call target here, so that you can make a connection between this call side and this procedure header here, basically, and also this call side and this header. And this is also what this is all about when we're talking about call graphs. So call graphs, they basically give you this property. So while in the previous lecture, we were talking about this setup here, where we were analyzing a single method with respect to a property, and we were given an answer of whether that property holds or not at a given statement. In this lecture, we will be talking about interprocedural analysis. And like I said, the most important data structure to conduct such an interprocedural analysis, or eventually even a whole program analysis that covers the entire program, that is the call graph. A call graph is basically a static abstraction of all methods that a program may execute at runtime. So methods in this graph are represented as nodes, and calls are represented as edges. And what's important here is that a call graph is still a flow insensitive representation. So it tells you which methods can be called at which statements, at which call sites, but it doesn't tell you anything about the order in which that may happen. Okay, so that is different from a control flow graph. Let's take a look at the simple call graph for just a simple subject program that I made up. So here we have some main method, which is basically instantiating an observer pattern. So we are creating some subject, and we are adding some observers to it. In particular, we are adding a main class object itself, so that when we call modify here, and modify actually notifies observers, that will cause this update method to be called eventually. And now when you construct a call graph for this, it might look like this, just to show you an example. So obviously there's a node for the procedure main and class main here. Then this will actually have a call to the initializer of main. So that is nothing else but the constructor that's being called here. So in representations such as Jimble, for instance, and also in Java bytecode, this is usually represented using this init method name here. So this represents this constructor call. Then we also have the constructor call for subject here, and also we have the call to add observer. And of course, we have the call to modify, which resolves to this method here. And therefore, this can actually also call set changed and notify observers on a type observable. And in that particular observable that we have here, which is basically the which is main, we actually will call this update procedure here. Okay. Now, this was simple enough. What I already told you about is that in many languages you have so-called virtual method calls, or the notion is very much related to what is also called polymorphic method calls. So polymorphic method call is basically one that can have multiple possible call targets at runtime. So you don't know exactly which procedure is going to be called when the method call is happening. And in most languages, that can happen exactly when you have a virtual method call. In languages such as C or C++, you could even also have a function pointer that can also be polymorphic, because the call target can also be replaced. So let's take a look at this example program here. So we are instantiating a collection using this make collection helper method here. And depending on the runtime argument here, depending on whether that is a list or not, we will instantiate a list or a hash set. And if you look at this program statically, you have no way of knowing what this argument may be, right? So we cannot possibly determine whether the returned object will be a list or a set. But then nonetheless, we are calling this add method on that object that is returned there. So a call graph for this would certainly have a call edge from main to make collection, but then it will also have to have a call edge for this add call here, and we don't really know where it's going to, right? So to be conservative, a call graph will then include all the possible edges to all the possible concrete target methods. So in particular, note there's no edge to a method, let's say collection.add or anything like this, because such an edge wouldn't really be very helpful. Collection.add is just an interface. It's not an implemented method. So it doesn't really make sense to analyze it. What we really want to express is that any possible implementation of that interface could be called here, right? And so it makes sense, for instance, to add such edges like you see here to these potential call targets. And there are different algorithms that allow different precision here in terms of which call targets are being selected. And this is what I'm going to be talking about mostly in this lecture this week. So let's take a look at a call graph more generally. So if we look at such a graph here and we assume that this is our call graph, then first of all, such a call graph will have entry points. So often you are in a situation where you only have a single entry point. So for instance, your program's main method, that's where your program starts. But let's say you're analyzing a library in isolation, or maybe you're analyzing an Android app that is actually you can say an Android app is a program that actually plugs into the Android framework. So it doesn't really have a main method. It's rather being called at different events that happen on your mobile phone, then these programs or libraries, they will have multiple entry points. Um, but then you have methods that are reachable from these entry points. And what you see here is that there are some methods that have potentially polymorphic call sites, right? So these are call sites that have multiple call targets, right? So this one is not polymorphic because it has only a single call target. So this is fixed, or you can also say it's static. It's monomorphic. That's another way of putting it. But these are polymorphic because you don't really know, is the call going to go here or there? Okay. And now using call graph analysis, you can improve on this call graph. So for instance, we could figure out using call graph analysis that all of these red methods here, they're not actually reachable, right? Because at runtime, we can figure out, or statically, we can figure out that at runtime, you can only ever have these black call edges, but not the red ones. Okay, so this call is not actually possible. This one is not possible. This one is not possible. And this entry point is maybe not even valid. And then that means that this entire part that's basically dead code. It's not reachable. And so is also this code not reachable. And now what you also see is that all of a sudden many of these methods that previously were polymorphic, or many of these call sites that were polymorphic, so for instance, these ones here, they now all of a sudden became monomorphic, right? So by eliminating some of this unreachable code, we have now determined that, for instance, this call site here, it will always actually call this procedure, and this will always call this procedure, right? Now you can imagine why is that actually useful, right? So this has several uses. So first of all, it can make the analysis as a whole more precise because if we can sort of shrink the set of procedures that we have to examine, then this can lead to the fact that yeah, we in the end we only end up analyzing that fraction of the program that can really execute at runtime. And if you put it the other way around, if we didn't do this, then we would always also analyze possible runtime paths that can never actually occur at runtime. And of course, that would then lead to analysis information that is spurious, right? That doesn't really make sense because it cannot be realized as you run your program. But another interesting point about this is that once you have determined this and you have actually determined that certain call sites are monomorphic, then you can actually specialize them and you can create what is called a pruned program, right? So here, for instance, in the extreme, you could replace these virtual method calls by static method calls. You could now even inline some of them. So inlining is optimization procedure where you are sort of copying code of callee procedures into the caller procedures to make the code more efficient. So this is something that can facilitate inlining. And you can, of course, shrink the code, right? So there's code that previously wasn't really reachable. So you don't need to ship that with your application in the first place, right? And that can, for instance, depending on which kinds of programs you're talking about, can even minimize the program's attack surface. So for instance, for binary machine code, there are so-called code reuse attacks that make use of code that is even unreachable in your program. And if you can minimize that amount of code, that can make your program actually more secure. So in the end, we want to minimize the number of reachable methods, or we want to determine the smallest set of actually reachable methods, let's say. We also want to minimize the call edges and the potentially polymorphic call sites. And like I said, there are a number of approaches that let you do this, and there are also a number of algorithms that are very popular and that I want to cover this week. So some very basic one, which is called CHA, and then there's rapid type analysis and variable and declared type analysis. These two are very similar. They are variants of one another. And then in the end, I will also talk about a general framework for constructing these kinds of analysis. And this framework is embedded into Suite, and it's called Spark, and it allows you to use all of these algorithms and also implement your own variants of them if you like. In LLVM and Phasor, there is slightly similar support. So you will see a lot of resemblance on that level as well if you're using Phasor as your analysis framework of choice. Let's talk about class hierarchy analysis first. So this is the most simple of the analysis that I'll present, and I would say it's actually also the most simple one you can possibly think of. So here the idea is that for a polymorphic or virtual method call site M, right? So where some procedure with the name M is called on a declared type T, right? So we're calling T.M. We are assuming a call edge to any possible subclass of T that implements M. And this includes T itself, right? So unless T is an interface. So let's take a look at an example. So for instance, here's the example we had earlier where we are actually instantiating either an array list or a hash set. And we are instantiating only these two, right? But now let's take a look at what the CHA actually does. So CHA, like I said, it's assuming any possible subtype of the type that is actually being called, and the type that is being called here is a collection, right? So that is the declared type here. That is T, basically. And now we have to consider any possible subtype of T or subtype of collection here that actually implements this add method. And unfortunately, there are quite a few, right? So you will not only be picking up array list or hash set, but also things like linked hash set or entry set and so on. And if you actually take a look at the entire type hierarchy of collection, this is from a few years ago, maybe there are now even more classes. You will see that there are many dozens, right? And this even goes on and subtypes and so on. And all of these need to be considered. Obviously, that's not very precise at all, right? Because for this program here, we saw that there can actually only be two possible call targets at runtime. But here we are assuming a few dozen of them, right? And many of them are actually spurious results. So the good thing about CHA is that it's very simple, and it always also gives you a correct answer, right? So the call graph definitely contains edges for all calls that the program could execute. So you're always guaranteed to get a sound answer. And what's really nice about it is that it has very few requirements. So you only need to know the class hierarchy information, which is something that usually you always have access to. In particular, you do not need to know anything about which types are instantiated or how they are being assigned to certain variables, which is a requirement for most of the other algorithms that we will be talking about. So that means CHA you can always apply. You can apply it when you're analyzing a library, for instance. You can apply it when you're analyzing a framework and you don't really know which types are instantiated. So that makes it very versatile. But the bad thing is obviously that it's horribly imprecise. So most edges will actually never be executed in reality. So it gives you a nice sound upper bound, but often it's not much more useful than that. But the next best thing, and that's actually a big booster, let's say, is actually rapid type analysis, RTA, which is very similar to CHA, but it only takes into account types that are actually being instantiated in your program. So let's take a look at this program again that we had before. So like I said, it's actually the same as CHA, but now it looks at which types are actually instantiated. And here you are instantiating the type array list, for instance, and you're also instantiating the type hash set. So that means if we now consider this, and the analysis really works by doing a linear scan through your program and simply looking at which types are instantiated anywhere, right? So it doesn't even look at, can this allocation here reach this variable? It's not even considering that. It's just linearly doing a syntactic scan of your program, looking at what is actually ever being instantiated anywhere. And by looking at this, it now knows that this can possibly only go to ArrayList.add and hashset.add and not to anything else because no other type is actually being created. Okay. And just to make sure you understand, so I could even have something like this, right? So I could even have a instantiation of linked list.add and of linked list here, and I don't call add on this object ever in the program, right? But nonetheless, just because this instantiation exists somewhere in the program, we will assume that this add call nonetheless can also go to linked list.add. Okay, so that's where RTA is not optimal then, right? So certainly it gives you more coarse grain information than possible, right? So there are still imprecisions that this causes, like you see here, but it's already a lot better than CHA because, like in this little example, you're already seeing that we have cut down the call graph a lot. And there are actually statistics that show that in many cases, RTA is already good enough to get rid of 70–80% of the spurious calls that you would normally have in your call graph. So what's good about it is it's still pretty fast. That's also why it's called rapid type analysis. And it really has linear complexity in the size of the program, right? So you're just doing a linear scan, syntactic scan through your program, not looking at assignments or anything. So that's pretty cheap. And it's much better than CHA, and it soundly ignores many types that are never instantiated. And therefore the call graph is much smaller, but it's typically still correct. There is one caveat there. Some of you may know that languages such as Java, they allow, for instance, for what is called reflection. So reflection is a feature that allows you to instantiate certain types and also doing method calls on them without actually having these explicit type names in the code. That can be a problem even for RTA because then it cannot figure out exactly that this particular type is being instantiated. And then you need some special treatment for this. But there are approaches to deal with that. And in DECA II next term, we will actually be talking about that as well. Another more structural drawback of RTA is that it does not actually consider assignments at all. So this is by construction, right? That's what makes RTA so rapid. It does not look at assignments, but that is also a source of imprecision. And there are algorithms that do consider assignments. They basically use a lightweight form of pointer analysis. And the first one that I want to discuss today is called variable type analysis. That actually takes variable assignments into account. And we'll be discussing that after the next break.